Welcome to Sampling Distributions. Today we are going to tackle one of the most important concepts in statistics, type 1 and type 2 errors. Imagine you are a judge making a critical decision with imperfect evidence. How do you weigh the risks of making a mistake? By the end of this video, you will understand exactly how statisticians balance these risks and why this balance is a matter of life and death in fields like medicine and engineering. Let us dive in. To understand statistical errors, we first need to understand how we set up a test. Think of a criminal trial. The law assumes a defendant is innocent until proven guilty. In statistics, this default assumption of no effect or status quo is called the null hypothesis, written as H0. The alternative hypothesis, written as H1, is the new claim or the guilt we are trying to prove. Because our evidence comes from a limited sample, not the whole population, we can never be 100% certain. This uncertainty means we are always at risk of making two very specific types of mistakes when we make our final decision. Now that we have our hypotheses, let us look at the first mistake we could make. A type 1 error happens when we reject the null hypothesis even though it is actually true. In our courtroom, this is the tragedy of convicting an innocent person. In everyday terms, think of it as a false alarm. It is like your smoke detector going off when you are just boiling water and there is no actual fire. You took action, but there was no real effect to react to. This is a critical error because it can lead to wasted resources or unnecessary panic. This brings us to the mathematical side of a false alarm. We denote the event of making a type 1 error as E1. The probability of this event occurring is represented by the Greek letter alpha. We also call alpha the level of significance of our test. It represents the maximum chance of a false alarm that we are willing to accept before we even begin. For example, if we set alpha to 0.05, we are explicitly accepting a 5% chance that we might accidentally reject a true null hypothesis. If alpha increases, we are allowing more false alarms. Having established what a false alarm is, we must now consider the opposite scenario. A type 2 error occurs when we fail to reject the null hypothesis even though it is actually false. Back in the courtroom, this means accidentally letting a guilty person go free. In everyday life, this is a missed detection. Imagine a smoke detector staying completely silent while the kitchen is actually burning down. The effect is real, but our test completely missed it. Depending on the situation, a missed detection can be just as dangerous, if not more so, than a false alarm. Just as we quantified the false alarm, we must quantify the missed detection. We denote the event of making a type 2 error as E2. The probability of this happening is represented by the Greek letter beta. Beta is essentially a misread. It tells us the probability that we will fail to detect a real effect when it actually exists in the population. Unlike alpha, which we usually choose ourselves, beta is harder to pin down. It depends on several hidden factors, especially how large the actual effect or difference truly is. A higher beta means a higher chance of missing the truth. Now that we know our miss rate, we can talk about our success rate. This is called the power of the test. Power is the probability of correctly rejecting a false null hypothesis. It is the exact opposite of making a type 2 error. If beta is the chance of missing the fire, the power is the chance of successfully detecting the fire and sounding the alarm. Naturally, as statisticians, we want the power of our test to be as close to 100% as possible, ensuring that if an effect is there, we will definitely find it. Let us look at the simple formula that connects these ideas. The power of the test, denoted as PW, is exactly equal to 1 minus beta. Because beta is the probability of a missed detection, subtracting it from 1 gives us the probability of a successful detection. Conceptually, this means that if you want to increase the power of your test, you must find a way to decrease beta. If beta goes down, the power goes up. They are two sides of the same coin when it comes to detecting a false null hypothesis. This formula we just saw leads us to an important question. Why not just set both alpha and beta to 0? Unfortunately, for a fixed sample size, these two probabilities have an inverse relationship. They act exactly like a seesaw. If you decrease alpha to avoid false alarms, you demand overwhelming evidence before taking action. But by requiring such strict evidence, you will inevitably miss some real effects, which increases beta. To decrease both errors at the same time, the only solution is to gather more data by increasing your sample size. Let us visualize this seesaw effect to make it perfectly clear. On screen, you see two overlapping bell curves. The left curve represents the null hypothesis and the right curve represents the alternative hypothesis. The dashed vertical line is our decision boundary. The red shaded area to the right of the boundary under the first curve is alpha, our type 1 error. The blue shaded area to the left of the boundary under the second curve is beta, our type 2 error. Notice how moving that vertical line to the right shrinks the red alpha area, but automatically forces the blue beta area to get larger. The green area represents the power. Before we move on, let us see this with a concrete example. A doctor is testing a patient for a rare disease. The null hypothesis is that the patient is healthy, and the alternative is that they have the disease. We are told the test has a 5% chance of a false positive and a 10% chance of a false negative. Our goal is to identify the error probabilities and calculate the power. First, a false positive means diagnosing a healthy person as sick. This is rejecting a true null hypothesis. So alpha is 0.05. A false negative means telling a sick person they are healthy, which is beta at 0.10. Continuing with our medical test, we now have our beta value of 0.10. We need to calculate the power of the test, which is the probability that the test correctly identifies a sick person. We use our power formula, PW equals 1 minus beta. Substituting 0.10 for beta, we get 1 minus 0.10, which equals 0.90. This means the power of the test is 90%. In physical terms, this medical test will successfully detect the disease in 90% of the patients who actually have it. Let us look at a second example, this time in a factory setting. A factory produces light bulbs, and the null hypothesis is that a batch is good. The manager currently has a strict rule where alpha is 0.01 and beta is 0.20. To avoid shipping bad bulbs, the manager changes the rule to decrease beta to 0.05. We need to calculate the new power and explain what happens to alpha. We start by noting the new beta value. The rule has become more sensitive to catch more bad batches. Continuing with the factory example, we calculate the updated power using the new beta of 0.05. 1 minus 0.05 gives us a new power of 0.95. The factory will now successfully catch 95% of the bad batches, up from 80%. However, we must remember the seesaw trade-off. Because the manager decreased beta from 0.20 to 0.05 without increasing the sample size, alpha must increase. The manager will now experience more false alarms, accidentally throwing away perfectly good batches of light bulbs. We have covered a lot of ground today, so let us summarize the key takeaways. First, a type 1 error is a false alarm, where we falsely reject a true null hypothesis, measured by alpha. Second, a type 2 error is a missed detection, where we fail to reject a false null hypothesis, measured by beta. Third, the power of a test measures our ability to correctly detect a real effect. Finally, alpha and beta have an inverse relationship. Decreasing one naturally increases the other unless you gather more data. Understanding this balance is critical for making safe, data-driven decisions in the real world. Great job following along.